Am I audible?
No, I think you need to use this.
Okay. This I have two.
Yeah,
So what is this for?
that is for recording.
Okay.
This is, you can maybe.
This I can put here, maybe.
Yeah, perfect.
Audible now? Yeah, thanks. So, myself, Sounak Dey. I am a senior scientist in TCS Research. I am leading the Neuromorphic computing research and activities in this group. So, we are one of the co-sponsors of this BNEW workshop. Today, I will talk about our whole journey from the last 5 years, where we have worked on different applications using spiking neural networks and tried to put them on different kind of boards and all. So I'll talk about that. 3 of my colleagues are already there. They're attending there, Diganchal, Bernali, and Shan. So before I go into my detailed technical talk, this is a brief overview of TCS. We are one of the largest software organizations in India, and we are located across global we have global presence. And in TCS Research, ideally, we have 3 pillars: TCS Research, TCS Coin, and TCS Space. In TCS Coin, it looks into the extended ecosystem, including the academia, startups, etc. And TCS Space is more towards like market-oriented, customer-oriented. They show demos and they have setups in different places. So these are some figures that represents our research activity. And these are the global presence. If you look at that, we have startups, 3,000 startups we have so far tied up with, and 66 academic institutions so far. And these are the few prominent institutes across the globe that we are part of. We have Coin partnership with. And this is the research structure. This is the research domain that TCS Research mostly focus on. There are other parts which are not mentioned here, and we sit right at there in the yellow box, edge and neuromorphic computing. So coming to that, this is what we do mainly in Neuromorphic Research Group. So if you look at this pipeline, this is a generic pipeline of any spiking neural network architecture or workflow. We work on encoder, we work on N to a CNN, we work on SNN layers like different architectures and learning algorithms, neuron models, etc. And then we focus on different kind of data and different kind of applications based on that, like classification, segmentation, etc., pattern recognition. So these are the tasks that we do. And to create applications for gesture action recognition, time series classification, image segmentation, lossless data compression, anomaly detection, etc. On hardwares, like we are tied up with brain chip Akida. We are closely working with Intel. We are also working on FPGAs, and we have a IMC chip with IIT Delhi. And we publish at different places like this. So coming to our first work, this is very interesting with, that it came in line with my earlier speaker who said that a controlled chaos may improve your system. So this is one of the cases that we found where the base encoder that we had, Poisson encoder, rate encoder that we use normally in spiking neural networks, we have seen it performing like very well. B means base encoder, which is Poisson, giving you this kind of accuracy on MGS or different other time series data. Now what we did is, in the data, we have added a small amount of noise. The noise goes like this, the noise sigma goes like this, and we have measured the mutual information score between the output spike trend and the input data, input time series. So that way we found that the mutual information increases like that, and then it falls like that, which means we have to find a sweet little spot over there which gives you very optimal, or I would say maximal, mutual information content, which means you are sending more information content into the network with an expectation that the network will perform better, and which is happening actually. If we do that kind of noise input into the signal, we get, this is mutual information based performance. You see, in every cases, we are getting a improvement over the existing Poisson or rate encoders. So this is one of the interesting works we have done on univariate time series data, starting on four such time series publicly available. Then we have extended this into multivariate also. And there we have found similar kind of results. So this is really interesting. This encoder, which is sitting on top of classical Poisson encoder with an addition of noise input, can be pluggable into any neuromorphic hardware. Usually neuromorphic hardwares have their encoders inbuilt, their learning algorithms inbuilt, but if they allow us, this can be a pluggable unit to those. Coming to our next work, this is our first work that we have done with BrainChip. They have a board called Akida 1000. At that point of time, it was Akida 1000. Right now, they are coming up with a lot of boards like Akida 1500, Akida 2000, etc. So this was done in real time. It has been demoed in NeurIPS 2019, I guess, yeah, where we have used a DVS camera in real time. The network was learning the gestures in real time. Somebody was moving his hand like this, that, like this. And then it is sending the instruction to the robot, and the robot was moving in simulation, of course, forward, backward, turn left, turn right, etc. So the key part is, if you see, it consumes less than 3 milliwatts of energy. And it takes very less, 3 seconds only, to learn each gesture. Many people came to our stall and they have taught this system, and they found that different gestures for different movements of the robot. It happened, really. Inspired from this work, we have designed our own spiking neural network, which is a convolution-based spiking neural network. It was very complex, we must say. It had multiple layers of feed-forward architectures and then a set of reservoirs. And then finally, we have tested it on 2 datasets. One is IBM DVS dataset, and one is generated in our lab using radar, where few people were performing some actions, and the radar rays were thrown to them, and the reflection has been captured, and that reflection has been binarized. The spectrogram has been binarized and has been fed into the network as an image. So these 2 things were tested using this network, and we got quite good accuracy. The one observation we found here, in IBM DVS gesture dataset, we had 2 gestures. So one is like rotating clockwise, another is rotating anti-clockwise. So this network could not identify these 2 because it couldn't identify where it is starting from and which direction it is moving. Somehow it failed. So it couldn't identify between these 2. Our gestures were perfectly recognized. So it is more like spatial, and we expected that reservoir would contribute to the temporal part of the gesture, but it didn't. So that was a learning from this network. In the gesture domain, we have extended our work in 2 other areas where we have used a very naive laptop speakers and microphones, where you move your hand in front of your laptop speakers, and the speaker sends some ultrasound wave, and it gets reflected, and the microphone captures it. And using that, we do some signal processing up there, and then we have a CNN model which tries to classify which gesture it is, or even if you write in air like G, A, etc., which are very useful for people who have disabilities and all. So these kind of CNNs then have been converted into SNNs using Akida's workflow, and we have run it on Akida board, and those are the results we found. If you see the, yeah.
Where is the ultrasound coming in here?
Ultrasound has been, coming out from the speaker of the laptop. We have tuned it like that. And the reflection has been captured by the microphone of the same laptop speaker. Pardon?
What are the frequencies?
Frequencies in the ultrasound domain, of course. So I'm not sure about the exact.
Ultrasound is anything greater than the
Yeah, not way much. Normal ultrasound, not like bat-like thing. I'm not that sure about the frequencies. Because I not sure about this frequency thing. So yeah, sorry about that. Yeah, I can come back to you after if you allow me. So these are the works. So it says that if you see the synaptic operation, which we measure as a performance metric of a spiking neural network, if you see it is 35 million, while that for CNN is 95 million, which is like matrix addition and multiplication, MAC operations. So this is the benefit we could show at that point of time. Then again, coming back to time series, these are two important work that we have done, focusing on practical applicability of putting a neuromorphic hardware, maybe it is futuristic, putting a neuromorphic hardware into your pacemaker so that you can, in real time, classify whether something is going wrong or not. Like you said, sir, that RR interval, this work is based on PQRS and this RR interval also. So we have tested it on MIT BIH, PhysioNet, all these standard data sets, and we have got quite good accuracy. We didn't take it to Akida. We didn't take it to Loihi. It is still going on. We are working on it. But in simulation, using BindsNet, at that point of time, we used to use BindsNet as a simulator in our lab. Using BindsNet, we got pretty good accuracy. And same thing happened with EEG, where EEG is a very cryptic and very complex data to handle with. I mean, but after some noise reduction and some pre-processing, we could at least found that that figure is not perfect. It's more than that, 75% accuracy on EEG MET dataset that we have done. So these are on time series. And then we have taken one industry use case of predicting the machine condition, where a machine is vibrating when it is in its lifetime, and you need to figure out when it needs a maintenance by monitoring the vibration time series coming out of the machine. It is applicable for larger machines where you cannot really go every day and see what is happening inside. So there, see this is that graph where the normal vibration is coming out from the machine, and then after a certain spot, it goes down. So you have to find out this particular spot. So there is a stark difference between the earlier time series part and that particular time series part, and we have to classify that. So it is and you have to do it in real time. We have designed one reservoir-based spiking neural network, where we have tested with existing edge solutions that used to work in predictive maintenance cases. And we found ours is working very well. The interesting part that I would like to draw your attention to is that if you see for the Ford A, which is a vibration data set of engine, Ford B, Ford A, both are like that. If you reduce the training data set from 100% till 20%, we have done that. You see the accuracy doesn't fall that much. We are not very sure about the reason, but does it indicate that time series are learned very fast by spiking neural networks? Is it the conclusion? I am not very sure. We are not very sure, but we are still about to experiment more on this. But this is one very interesting observation and indication that it needs to be looked into. That even if you reduce your training data so that your training time is less, your training data is less, but still you are getting desired performance, at least not very bad, from 79% to 74%. That much drop is only there. Extending this reservoir-based architecture, this is the time series prediction work that we have done. A probabilistic reservoir coupled with an encoder and force learning. This is the total architecture. And we have tested it on different kind of stationary, non-stationary, all kinds of time series data. Some practical, some synthetic. 9 data sets, if I'm not wrong. And in every case, we have found that ours is giving very good R2 score. R2 score. And we have compared our work with SARIMA and Stack LSTM, which are our competitor. And we found that R2 score wise, mostly our work is comparable with them, but the benefit is here. We do not require any buffer memory. So that way, we are not using any memory in the system, and if we can implement it on a hardware, you are saving a lot of time, a lot of memory that way. So you do not, at least 6,000 for, sorry, that is that there is no figure, numeric figure, yeah. So it is not using any memory. Now, again, extending this work to multi-sensor fusion, coming different time series, coming from different sensors together, and you have taken a case of fault detection, which is very obvious, which can be done within the periphery of your home, where you can put different sensors. You can carry a phone where there is accelerometer, gyroscope, etc., and then you can merge them together to find out whether a person is falling or not. So this work is our first work using spiking attenuation network. We have compared our work. We didn't find any other prior art here, so we had to compare with the classical CNN. And we have tested with non-spiking convolution and spiking convolution both. And the results shows that ours is working pretty well, accuracy-wise. DSCS is this dual stream convolutional neural network with self-attention. That is the present prior art on fault detection, which is giving you the best results. And obviously, we have compared the MAX and the SOPs there, which is giving pretty exciting figures. And if we put it on Loihi 2, we can estimate how much energy it will consume if we implement this network there. So we have not implemented it, of course, but the paper gives you the exact figures. So by that, using that, you can estimate what exactly you're going to consume. Obviously, there will be some difference when you actually put it on the board. Another interesting use case that you have tried to attack is deep brain stimulation. Here, it is a classical edge case where you need to monitor your brain signals, actually local field potentials, which is an output of a group of neurons that are there in the brain. You put an electrode there, you capture the data from there in time series mode, and then in real time, you figure out what is going wrong, especially for patients like who have Alzheimer's or what is that? The other Parkinson's, yeah, Parkinson's and Alzheimer's. So there you capture the local field potential, you measure what class it belongs to, either bad or good or maybe somewhere in between, and then you, in real time, you decide how much input has to be given to the network so that it behaves well, so that the person is going to fall, you predict it, he is going to fall, and then you give him the certain signal using that deep brain stimulator system so that he doesn't fall. Your fall is stopped. Yeah. Pardon? It is invasive. So it needs a lot of experimentation and all, but these are very initial experiments using local field potential, that whether we can first of all classify it or not. Then we'll predict how much input needs to be given, and then the whole system. It depends on the hardware. Usually what happens now is they capture the LFP, they send it to another computer, and then calculate and try to predict what is going to happen next, and by that time the person falls. It is not practical. It is good for medical research and all, but it is not good for practical use. So we are trying to do that. It will take time. These are some initial exciting results. Now, this is one example of the COIN partnership with Premier Institute. We have given one project to IIT Delhi, Professor Manan Suri. He is designing one in-memory chip, in-memory computing chip, IMC, where we are trying to put a very small memory, 4-bit kind of 4-bit processing capability it has, a GRU unit, which will do anomaly detection. What is the target? If you have any time series that is coming into your system, we have a use case like detecting hacking in real time. If you have an edge device and somebody tries to hack it, then he sends a set of packets. We consider them as time series. We try to find out if there is any anomalous packet inside that time series so that you can identify in real time whether your device is getting hacked or not. At least you raise a flag. In our mobiles, in our pacemakers, in our wearable, we don't have any such protection mechanism, right? All we have is an antivirus max. So if somebody wants to hack you, you can raise a flag at least. So this is the target of this project, where he is designing the hardware and we are designing the software. We have made it quantized, made it tuned, made it possible to put it on that board. And then finally we have put it on the board last month actually. And this is giving us good results. So those results are not updated, I'm sorry, but good results are like it is running and it's giving 89% accuracies on identifying any anomalous packet on standard data sets. This is one interesting use case where, again, it came from one of the TCS customers who wanted to identify whether a person was yawning or looking away or closing his eyes while he was driving, because it came from insurance. They didn't want to pay the customer if you are looking away and made an accident. If you are sleeping, I don't want to pay you. So those causes where they wanted to identify, and we have put a camera on board. So this kind of network, which will capture in real time whether the person was sleeping or looking away kind of stuff, whether he, these are the example images that we have tested with. The interesting part that we have observed is we have 4 classes there, like I have mentioned. We have 4 classes there. Yawning, closing eyes, maybe putting his hand on your mouth, and something another. So we have tested, we have trained this model with 3 classes, and then 1 new class is added on board. So during simulation, these 3 classes have been taught to the network. It has been implemented on the board. Then we have added 1 more class. And you see the accuracy is not dropping that much. So this new class is learning on board. And that really opens up the avenue of customizing your solution. You can train new classes. We have tried with 2 classes also, 2 classes, and then train 2 new classes there, and see the accuracy is dropping. Obviously it is dropping, but still it needs more investigation so that we can improve upon the results. But it opens up the avenue of customizing and learning new classes at the edge after implementation. These are 2 interesting use cases that we have done with European Space Agency. European Space Agency came up with a problem challenge that can you do something intelligent in the space, sitting on the satellites, where satellites observe the ground or the Earth, they capture Earth observation images, and they send it to the ground. The sending window is very small, 20 minutes. It is costly in terms of communication and in terms of energy, because satellites run on battery or solar power. Now, if you put some intelligence on board on the satellite, they are called low Earth orbital satellites. They do not have any intelligence as of now. If you want to put some intelligence, then it means it will consume some battery. So we tried with neuromorphic computing boards, whether we can put some intelligence on the LEO satellite itself, where it can identify the image is garbage or not. Image is garbage is not. What do I mean by that is, if you capture an image, if it is cloudy, if you send it back to the ground station, it doesn't make any meaning. Either you have to do a hell lot of processing to remove the cloud, which is very compute intensive and time intensive, or you have to directly discard it. So that's why we tried to put an intelligent system on the board using brain chip so that it can be identified in real time whether the image is cloudy or not. Then we have done, what we have done is actually 2-stage CNN here, and we have cut the image into pieces. Like you see, the stage 1 output is like that. You do 3-class classifier here, clear, partly clear, and completely cloudy. and then you investigate more on these partly cloudy parts. You segment it more, and then find out whether it is really worth to send this image back to the ground station or not. If it is worth, then you have another provision which we have designed, a lossless compression. I'm coming to that. Now, if you look at the figures, we have tested it with, compared it with Jetson TX2, or the same capability, and that is giving us 230 times better, SNN on Akida is at least 35 times efficient compared to equivalent CNN running on Jetson. So it is like, you see the figures there. So that kind of efficiency, and the latency also improved 3.4 times faster compared to Jetson TX2. Now, once you decide that the image is good and you want to send it back to the ground station, then what you do is lossless compression on that image. If you decide, so on a normal day, if you capture 1,000 images, out of which maybe 50 are cloudy, you discard directly 50% of your data, which you save on a payload, and then on the rest, you compress it in lossless fashion so that you can send it, your payload becomes even less. So how much compression we are doing here? We have, this is the whole architecture that we have designed. The input image is there. We only send the boundary pixels. We predict the inside pixels using our SNN, and then we put the same SNN back into the ground station, which will predict out using the boundary pixels and reconstruct the image. So while you're doing that, this is the structure that actually there are RGB channels. You put it in like this, the red figures, green figures, and blue figures. You predict. You try to, using these 4 pixels, you try to learn what is this using your ground truth data, and then you send it to the network. The network learns like that. It predicts what is this 4th pixel is, and using the same thing, you actually predict, reconstruct the image in the ground station using only the boundary pixels. So actually your payload is becoming very less. On a normal day, it is like 25% of the whole payload, that kind of savings. We have shown this to the European Space Agency, and they are very excited. We are working with them to put it on board.
How much is the residual error percentage?
Yeah, it was there. I guess it was there in one of the images, no? It was not much. I mean, I do not have the figure here.
Because that is what is going through arithmetic code, I think.
Actually, yes, you're right, but the figures are not here, but I can tell you that I have a figure I can send it to, which is not widened that much from the mean. It is not that great. It is acceptable. Okay. So, other than this, we have done some works on implementing Koopman operator, which is very key component in any control systems using spiking neural networks. And we are trying to different other cases in space, where space debris collection, satellite docking, those are the cases we are looking into with different customers and all. Now, essentially what we have
or 1 mm?
Clearly this is working well, but nobody can challenge us that we are not avoiding the standard. So there is a gap. And if you want to create a network, if you want to create an application for a customer, for a practical use case, you have to learn a lot of things. It is not like you are designing a TensorFlow or CNN network. The tools are available. So essentially, what happens is end result is developmental delay, less democratization or popularity from developers and customers. So that is why the popular, it's a chicken and egg problem. Now, if you look at, I have taken this image straight from the Open Neuromorphic blog. So if you look at this, what I was telling you about this ML, classical ML stack is very well defined and very working very well. You need maybe 2-3 days to create a model and train it and test it and put it on the board. But for neuromorphic, it is not like that. The key problem is deployment. Here, Pine, NIR and NeuroML are the efforts that are being made right now. But still you have to go. This is the problem. Now, if you look at NIR or NeuroML is more cell network models like in biological point of view. So let's not go into that, but NIR, which is very relevant for us. I guess some of the participants or organizers are part of NIR, right? So what NIR does is it enables model interoperability and deployment. So if you take a case like this, I have a model here in SNM jobs. It will be standardized in NIR like this, and the equivalent part in Java is like this, and the problem version is this. It doesn't solve the problem of learning. It doesn't solve the problem of deployment. It doesn't solve. What it does is it gives you a standard framework that you write your network or you write your code following this. It's just a class definition, to put it in simple words. So, what is next? The model performance. Even if you write your neural models, if you design something on simulation, even if you write it in that structure or framework, I would say, it performance. If you get 80% accuracy here in a center, you will not get it in Java or Rock. So this is the this is the existing scenario to put in a broader way. You have something software simulated, you do the NIR mapping, then you map it to different hardware specific models, then you have to retune it. So this is an or you have to know this mapping. You have to know what is happening inside it. And then you can deploy. So it is time consuming and learning consuming and delay. It brings in delay. What we are proposing is, our thoughts is like, you create a hardware existing model here, tuned and well performing, put it in Neuromorphic NIR meta model. We do not bypass NIR because this is standard. So we put some extension here in NIR, we are trying to do that. And we are trying to put something on the simulation side also, so that it becomes NIR friendly and hardware friendly. We are directly trying to put it on the hardware without the effort of retuning. So that is our thoughts and our contribution is going to be. We are not claiming that retuning is not required. Retuning is optional, like I have mentioned here. But what it brings in is hardware specific features are abstracted so that conversion performance. So you are guaranteeing the performance. That is our thought. And obviously it will be easy to deploy, and retuning is optional. So those are the benefits we are trying to bring in. And this is the very abstracted, we have already patented it, the idea and some implementation. This is the very abstracted idea of our neuromorphic middleware that we are thinking. You take different use cases, like the stack I have shown from the Open Neuromorphic blog. There, we are trying to create a complete toolchain till the hardware level, so that you come up with a use case, you take the user input via CLI or maybe a simple UI, then you use our tools, our models, which we have a large pool of models, like I was showing you. Architecture libraries, learning algorithms, simulation tools, etc. All these will be there in the middle, and then we are putting this NIR compatible tool chain abstraction. The idea is going to chain provider or the hardware provider. If Loihi is coming up with Lava, if Sensen is coming up with Rockpool, BrainChip is coming up with Akida MetaTF, let it be like that. We are handling the complexities here so that the developer doesn't need to worry about that. So that the time to deployment is reduced to a lot. Initial results, as you can see, before that, I just want to explicitly mention what are the key takeaways for developers and chip vendors. Obviously, for developers, extensive models we are offering, working on different data types, different architectures with acceptable performance. You can retune it as per your purpose, or you can reuse it as it is. The faster UI CLI-based development, less cognitive load. You don't have to worry about what is happening inside. Like you do not worry about what is happening inside the TensorFlow or CUDA, what is happening. Those kind of stuff you don't worry. And obviously there is a reduced learning curve, less neuromorphic expertise is required. You don't need to know even what a leaf neuron versus lava's player versus what is this, what is that. You don't need to know. If you are interested, of course you are welcome, but for democratization purpose, this can work. And for OEM chip vendors, what we are offering is Ring platform. Wide scale adoption without using your secrets. You are not using your secrets. Your toolchain remains intact. We are working on that. We are creating that for you so that your board becomes more popular across the community, across different applications. And the portability becomes very big. And so this is the second one, model portability. Essential for system integrators like us. We have customers who ask for, I have this much budget, I want to put this board, I have this much real estate on the machine. Do you have this solution? I say that I have that solution on this board. I have to redo the whole thing to get 6 months. No, I cannot say. So this is a benefit for us also. And beneficial for hardware OEMs who doesn't have a stack. Like for example, this identity case. They have their ISP, they do not have a software stack. This whole middleware stack can directly be friendly with that and can help them. For all the startups who do not have the stack, we are going to be friendly with them. Now, some initial results, we have developed a multi-sensor fusion application that I have shown using this middleware stack, and we have reached up to 3% higher accuracy than the manual tuning, doing 10 days job. We have used this stack and we have got 3% higher accuracy. Second, a simple time series application, again predictive maintenance case, where it has been created in 2 days as opposed to at least 10 days using this middleware. On top of Java, accuracy drop less than 2%. And the same network has been ported to Rockpool within a day, where it will take 3 to 4 weeks for a normal developer. The developer is sitting there, you can ask him, he has done that by hand. The Rockpool versus this porting within a day. This is the benefit. So I just want to highlight this. Our end goal is develop a working neuromorphic middleware stack. We are in the process of that. We are completing it. We have India-centric support for hardware developer, Indian Academic Institute. Anybody, if you have a stack, if you do not have a stack, you can come up directly to us and we can be collaborative with you. And more focus on hardware software core design, which some of us are doing. And obviously we are trying to open source our industry. We are doing so that maybe next year or next to next year, like this year, Innovator is doing it here, we are going to open source our middleware. We would like the developers here in BNEW to test it in real time. We will open our APIs and everything, and then we will test it and run the applications and see the benefit. So that, again, this is a team.